So with that, let me move forward. I want to just say that. Oops, that's a blank. That's a blank. That was I just put it there in. What I'm not going to cover is the time to event analysis. So, for example, most AD research really does time to something, and so so a good portion of that is time to death, time to dementia, time to something, survival analysis. And so I'm not going to be talking to that. I'm going to be talking about repeated measures design. And when Heather talked to me about this, I took this quote down. So, or I don't know whether it's a direct quote, but and so this is what this is to appeal to. It's talk to the residents and fellows, and with the approach that they're just starting in research. And so this is going to, if I can get away with it, I won't have any formulas here, or certainly we won't be doing much mathy things. And so my plan is to really talk for about 45 minutes and then leave 15 minutes for question and answers. And I've looked at the people on here, and I know that there are bunches of people who have this will talk down to. Some people who've taken my class, people who or people who actually work in this and have a long history of this. So I hope I don't put you to sleep with all of this. So that said, off we go. So what I will cover, I'm going to be living in the world of repeated measures, mixed models. And so I want to first talk about the use of mixed models and repeated measures in epidemiologic studies and in clinical trials. So I'll give some examples of that, and all with a bent towards studying using these models in for cognitive impairment research. So I'm going to talk about nonlinearities and splines, and then at the end of this, I'll talk about latent class trajectories, because that is the new hot thing in the field. That everybody, the new shiny object in the field is this latent class trajectory analysis. Okay, so any questions? Let me first also say that I hope that if you have questions, or if I'm not clear, if you please, I would really prefer for this to be a conversation. And so please interrupt me if you can or want. And then I also will say that most of the stuff that I will talk about as methods, if you are interested in this and you are brand new to Duke, or kind of finding a way through Duke, I teach the class in the clinical research training program on mixed models and survival analysis, but on mixed models. So if this catches you and you think it's great, then you come study with me for a semester. Okay, so let's look at the basic model. Having said we aren't going to have formulas and have here's a bunch of Greek so that we can start out. So the basic model given longitudinal data analysis has this kind of shape. So there's a beta naught. I mean, so those of you who have had a regression course, beta naught, of course, is there. And then you've got this thing called beta naught I. One of the things in repeated measures designs or in mixed models is that we oftentimes say we start out an individual and we give them their own little intercept. Notice the I. The I is, and there's the I there. The value for person I at time j is equal to some intercept plus the person's own little intercept plus beta 1 times time. So this says everything is going up or going down, plus beta 2 times x for the person I. So that this is kind of the starting model, and then we will hang things off of it all along the way. So let's use y as ADOS cog. So the ADOS cog for person I at time j is some function of time, and the predictor of interest, x. In a clinical trial, we oftentimes add 2 additional variables to the model. We add beta 3 is this interaction between x and time, so that we want to give different slopes over time for the individual. And beta 4 controls for baseline. So those of you who are going into clinical trials just know that this is the clinical trial model. The control for baseline it does something. Now I'll talk more about it, or I'll show what happens in a picture. But in a clinical trial, you randomize people to one group or the other, and the control for baseline will adjust for failures of randomization. It's not really failures, but and think about what it really is testing. Beta, this Y would then be, it makes everybody equal at baseline because you controlled them and baseline, of course, in the clinical trial is at the point of randomization. So this has that effect. It has another effect as well, and that is, what's the best predictor of what you're going to be tomorrow? It's what you are today. And so this will reduce variance, explain variance, explain the follow-up variables or the follow-up Y. The best is it's the best predictor of it. And so that has the effect of removing variance. Removing variance is good in all statistics, and or explaining variance is good in all statistics. And so what does that, why is that? Well, because when we explain variance, variance is in the denominator of everything we do. Explaining variance of F statistics, T statistics, chi-squares, it's in the denominator. And so if you have a denominator of a statistic that is getting smaller, that means the numerator is getting bigger. So our T's and our F's will be bigger. And then the nice thing then is our values then will be more likely to be significant. Okay, so that's the basic model. Now, I'll talk about this, but there are other issues that occur in a clinical trial, and I'll just raise them as for those of you who are using this mixed model in a clinical trial, and I'll show examples in just a few minutes, is first correlation. We have got, normally when you learned in Regression 101, when you started learning, you had, one of the assumptions was that things are independent. Here, things aren't independent anymore. What is not independent is, I've already alluded to it. The fact that your observation today is going to be correlated with your observation tomorrow. So these models are used for observations over time. So you're going to give an individual in your study will give you a bunch of observations, and there with that, then you have to deal with those independent observations and non-independent observations, and that brings you into discussions of how are they correlated. And so if you're working with your statistician, you'll find that there will be a lot of discussion of how are things correlated, and you're going to use that information then to adjust for the correlation. So in the extreme values, if you were a knucklehead and you studied the same thing over and over and over again, the correlation is 1.0. If I ask you your gender today, you're going to give me your gender today and tomorrow and the next day and the next day. So so if I study 100 people 100 times, 10 times each, I have 100 observations. I really only have 10 bits of data. I have, what you said your gender was the first time I asked you. So this adjustment is for what happened in whatever you're studying. You've worked hard to study people over time, and the question is do I have 10 degrees of freedom for the fact that I've studied 10 people one time, in essence, or do I have 100 bits of information because I've studied 10 people 10 times, and hence I have all and if they are independent, then I have 100 bits of information. So the correlation structure tells you about that. And second, missing values. Missing values are the bugaboo of clinical trials and all of this stuff. And so we spend a lot of time, if you are working with a statistician, we spend a lot of time talking about missing values and their impact on the answers. Now, I'll give you an example. When I was at Columbia, there was, in graduate school, there was a study ongoing, and it was in a clinical trial, and that we found we were studying people's symptoms, psychiatric for there were a bunch of studying the homeless in the big homeless shelter in the Armory across from the School of Public Health there, and we we had missing values. There was a drug trial ongoing, and half of these homeless people with who were had depression and symptoms of schizophrenia were allocated to drug. Half of them were drug allocated to placebo. And when we went to study missing values, the missing values had a huge impact. If you were on placebo, and then we had a huge dropout problem. If you were on placebo, you dropped out because you were coming in and taking drug, and it was a placebo, and you were just feeling crummier and crummier. If you're on drug, you dropped out because you started feeling better and better, and you thought you didn't need to comb anymore. And so the missing values were not at random at all, but rather were distributed differentially depending upon which drug you were allocated to. So let's study ADAS-Cog, and so in a clinical trial. Here's a quote from a paper down here. I've given you the reference to this paper. And it says, these data support a 3-point change in ADAS-Cog as being appropriate for MCRC in clinical trials of patients in early AD. So what does that really mean? When a clinical trial, let's go back to our model. And I've dropped for convenience this little intercept everybody gets. And here's the model. Can people see it? Is it big enough for people? Or I don't know what I can do to make it bigger, but I hope you can read. So is time, and then there at a simple level, there's a third value, which is time start drug. That's before. And so that it will show that the two groups are differing over time, that the two slopes are spreading across. I'll come back to my other point in just a minute, but let me show a drawing of it. A drawing of it would look like this. For MoCA and ADAS-Cog, these two continuous measures that people use regularly, this might be what this looked like. So that if you were on drug, it maintained your symptoms at some level, probably decreasing over time. But in the placebo group, the symptoms were increasing faster, and so your level of the ADAS-Cog was going down faster. So that that is this beta 3 in what I was showing before. Oops, come on. So that's this value. That's the drug by time. There is an interaction, so the effective drug is changing over time. And so in all drug trials, this is I shouldn't say all. As soon as I say all, something will happen, and that's not true anymore. But in most drug trials, drug by time interaction is the important variable. So this is how analysis occurs. As I noted before, typically this model gets expanded because we control for baseline, so there would be a B4 out here for the control for baseline, and then we would at the end of this make sure that the missing values weren't an issue. So are there questions about this before I move on? Okay. So there's the picture again. And so so a good example, so now let's move on to epidemiologic studies. Here's an epidemiologic result. It's by Krishnan, changes in Montreal, the MoCA over time. And so in a study of MCI versus normals, measured 3 years apart, MCI, which there are not 51 of them, showed a significant decrease in MoCA scores when accounting for age. The MCI group showed a decline of 1.7 points, while the cognitive intact participants remain stable. So if we go back to that drawing, which I was using for the clinical trial, there's no need. These two lines would be separated. They would be separated at the beginning, but the rapidity with which the MCI group was going down, or the trajectory of them would be larger in that group. in the MCI group. As an aside, back to speaking of the clinical trials, why are these 2 points joined there? Because you randomized, and so you typically hope that these 2 lines start for the 2 group in a clinical trial start at the same point, because you want to be sure and that any differential change is due to the difference between the groups that over time, changing difference between over time, and not due to something that they were at the very beginning. Okay, so the basic model in epidemiology is slightly different. Here we have, oops, I have double pluses here. Come on back. Forget that 1 plus. But you have the time, you have the x of interest, and then you have a whole bunch of covariates. And so the whole bunch of covariates is what tries to make the 2 groups equal, so that at the end of the day, the 2 people who differ on x, this beta will say on this x of interest will show up in the y's, and you have controlled out everything here, and the only difference between the 2 groups or the 2 people is due to the fact that they have the differences in the y's. And so let me show you a neat example of this, how it comes. Here's my cognitive impairment, and this is a study that I was reading because I'm now moving into COVID research, being dragged into COVID research. Report the outcome of 114 COVID assessments in acute respiratory stress survivors at 3, 6, and 12 months, and you can look at the change in the cognitive impairment. This is using a binary form of it, but you can see that the number of people going down in cognitive impairment or being cognitively impaired, labeled cognitively impaired, is going down over time. And so then this is So these sorts of things, these models are being employed now in COVID research. As an aside, my friend Charlie Hall, who's at Einstein, who has kind of my role at Einstein in the aging department there, he's now doing it. He's done a lot of work with this model, with these models in the 9/11 group. Because he's at Einstein, he can get down to Lower Manhattan and study the various people there, and he's got pictures and analyses that look a lot like this. But this is not MoCA, but he is studying these symptoms of these 9/11 workers who are survived. Okay, so the issue when we study in epidemiology is this idea of mediation moderation. So I will assume that you don't know mediation and moderation. So we'll say a few words about them. Mediation is this thing that says that with the variable in the model, it impacts the parameter for the variable of interest. So what this is that it says it's the mechanism model. You see that X is related to Y, but when you put Y, the mediator into the model, the effect changes. And so what that says is that if it's a true mediator, it says that the variable of interest X passes through the moderator on as it goes to Y, and so it has an indirect effect. So the total effect is actually the effect that as X relates to Y in a bivariate sense. The indirect effect is how it passes through something, and we use that in our work for example, how caloric restriction impacts outcomes, various outcomes. And so what is the mechanism by which it is that it happens? And for us, that is these metabolites is our study of that. In ADR research, you would think of it as being maybe education. So that if you looked at things that impact the slope, maybe it is in the moderator is something because people who are intellectually engaged are likely to have less effect, or the effect of whatever I'm doing that causes the change in the MoCA score, the ADAS-Cog, is partially mediated by the fact that people are reading or engaging their minds in various ways, and that's a big field in ADRD research. Some of you may be tempted to go into research in the EHR EMR, and that's the confounding by indication. The best example I've seen of that is some work that we were doing with depression when the Duke geriatric depression program was ongoing. We were looking at the effect of drugs on depression and using the EMR, meaning using the records that we got from the medical record. And we were finding that people who took drugs for depression had higher depression scores than people who didn't. Well, why was that? Because we were at that point, the study was observational, and patients were coming in when they felt crummy, and they would get a drug. And so what does that mean? Well, it means that people who got drugs had crummier, worse scores on the depression scale, and hence it kind of revert. Confounding by indication, we did not want to show that using depression drugs was related to higher depression scores. Missing values are the same problem throughout, and if I can convince you that you shouldn't do this alone, that you should seek adult supervision, find a statistician to do this to help you with this, then missing values the first thing you'll talk about when you do a mixed model will be talk about the correlation structure. The second thing you'll talk about is this bias that occurs when people have missing values. We assume that missing values are happening at random, meaning the person didn't show up accidentally, got lost, got hit by a bus, whatever, which are random events. But that doesn't mean that that always occurs. People who feel crummy don't come in and get investigated, and so their values, which would have said I feel crummy, aren't recorded. We had this problem in our Duke EPIs. We couldn't consent people who were cognitive impaired. Well, what happens is that we didn't get a measurement for them. What does that mean? That means that that their values weren't there, which were lower on the usual measures of impairment, which means then our numbers on the change in cognitive impairment were biased upward, meaning we gave a better estimate of what those values were than what the epidemiologic findings would be. Then we really had a right to. Okay, so now I want to talk a little bit about splines. So what we have, and splines are things that, because in general, when we study, our initial model was a linear model, but now we're going to say it's not necessarily a linear model. You can imagine that we could first say to ourselves that there's change, and that change is going to occur, and we could model that with polynomials or some sort of function that says that they changing over time. And so it's not a linear model, but there's change that needs to be added. Splines is another good example, a good example of this. And I'm going to talk about splines because in our research, in much of research, there is a change point, and people care about the change point. And I'll show two different reasons for that. So that's an old slide that shouldn't be there. So let's talk about compression and morbidity. And so the ideal for people in life is that you are totally functional. You go out and exercise. You work the New York Times crossword puzzle, and then you die quietly in your sleep that night. I mean, that's an ideal for people. In ADR research, it's that you don't become cognitively impaired until just before you die. So you continue to work the crossword puzzle, and then just before you die, and that's a good event. So there is this thing called compression of morbidity, mortality and morbidity, and I give you a reference to that if this topic interests you. But again, my friend Charlie Hall has used splines and used this idea of compression to talk about the change in cognitive impairment over time. And here he says, he asked the question, is there any difference? Is there something well, let me ask this first question. The general finding is that people become impaired 2 to 3 years, some anywhere from 2 to 5 years prior to their death, and that's it's seen as sort of a quality event, because people are living long lives and are only impaired for the final years. However, he asked the question, well, there has to be a change in slope, because people generally go along over time, and then they change slope. And so I show you what that looks like. And here's a good example, but this is going the wrong way. Here's the idea of a change in spline here going this way, where the person, if, for example, the measure of cognitive impairment we were measuring is it's going up, and here at time t, it changes slope, changes its slope. And so if we could measure where time t occurred, that could become a parameter that we could use. And that's exactly what Charlie is doing and has done, and what other people have done, is saying, if this change in slope is closer to the end of life, that's a good thing. If it's changed is way back here, then the person is going to live with cognitive impairment for a longer time, and that's a bad thing. So there's or this could be an event that the person that the person had an event like a stroke, and that changed his impairment. So we oftentimes don't know where this knot is. That's the change point, and but it could be due to a sentinel event, or it could just be knot could be with change in lives, but because people who use this. So it could be 65 at retirement, or it could be time varying, where everybody has their own change in slope. That's exactly the change, an inflection point for this. And so this would look like this. Person is an MCI. Here's a change point. Then dementia starts to occur, and this would be the end of life for that person. So you would hope that change point, we could move that change point up this way. So let me show you what Charlie did. And so here's the trajectories for everybody in this. This is known as a spaghetti plot, and it's most often we start by making these spaghetti plots. And here's the results for him. So if for people who are active, the green slopes are for people who are active. The red slopes are for people who are inactive. Well, look at what he found the best inflection point for each one of these people in this, where he's now counting backwards to death. This is the point, and he's taking this, and he calculates an inflection point, just as I showed in the prior slide. And he then asks the question, does the inflection point change depending upon whether your activity levels are there? And he maps where the average inflection point is. And so the inflection point for those people who are inactive is about 0.4 years different for people who are inactive versus those that are active. He's played this game with whole bunches of different outcomes. Those who have higher education, as their inflection point much skewed to the right, versus people who with a high school education is it skewed to the left. So this is what he's done, and it's so it's a really cool way if you're coming into ADRD research. Then this is a really cool way to study things. So So the research from the change point, and the change point becomes the issue, even though we're using even though we're using repeated measures to get the change point, but have that we can abstract that from the data, and we can ask questions like, do educated people have a knot or a change point that's closer to death, and does the ApoE4 allele make the knot more distal from death? The problem with what all this is that we're modeling it with this kind of approach versus we could put these kinds of approach, and it's a little difficult to distinguish between, is there true an inflection point versus is there just a function of time that is there? And so determining whether one model is better than other is difficult. These things are big data problems, and so that's, it's interesting that we can and we have to have a lot of data. If you look back at what Charlie Hall was doing, you can see that, he has a lot of people here that he's studying, and so he can play this game. And so if you can't really do this with small samples. And for the last bit, I was going to talk about latent class analysis, and latent class may be new to people. And so it's the new shiny object. I've said this before, it's the new shiny object on the block. And people walk into my office, nearly every researcher I know somehow says to me, I need one of these latent class analysis for my research. Everybody else is doing it, I want to do it too. So what is a latent class? Latent class is discerning patterns in data and that are not discernible using known predictors. We use regression to say, how well can I guess the line? But we may not have the predictors. If we have a group of lines or if we have a group of measures, latent class analysis says there are groups of people who tend to have lumpings of these variables that make them have slopes, or make them have measures that are high or low. And so this is the idea of saying there are different kinds of people, and I want to be able to disaggregate them, to make them, to classify them into various groups based on the measures that I have. And where that goes is you can, I give you an example of this where they were doing latent class analysis or latent profile analysis, all the same thing. Latent class identified 4 groups: moderate mixed dementia, mild mixed dementia, dysexecutive, and amnesic, using the neuropsych battery. So he was able to, and they were able to use this latent class analysis to typify people into various subgroups. And so, they used these kinds of methods. These methods are big data methods, but they are very powerful at the end of the day. But they also really require a statistician to help you. So again, more advice to seek adult supervision if you do this stuff. But I'm here to talk about longitudinal data and not just cross-sectional data. So let me talk about latent class trajectories. Here, you're asking the question, do people have different slopes? And so can I take those aggregation of slopes and of various classes of these slopes, saying here is a group that's high, here's a group that's low, et cetera. And I'm going to show 2 examples of this. The first is the latent class trajectory analysis, and here's the reference. And they found in this group of some small number, 200 subjects, that they found 1, 2, 3, 4, 5, 6 different slopes and types of slopes, looking for how people changed in the ADAS-Cog, MMSE, excuse me. And then so it said this is the result. And then the other thing they were doing was looking at what the probabilities are if you aren't in your group. What's the probability that you're in another group? So, for example, this group of people are more like this group than this group of people are than that group. And so this group, if in the classifications, these classifications aren't pure, that you don't see these slopes in the data. The program picks it out for you. So this is how the classification is really cool way of doing that. So if you do this, then 201 with possible Alzheimer's disease were evaluated for their cognitive and psychotic symptoms at regular intervals over 13 years. Cognitive were evaluated by the MMSE and psychotic symptoms by the CIRAD. And so this when they do that, they find these classes. Now, a note for you that this latent class trajectory is a big N problem. They and many statisticians advise at least 50 per group, and the smallest group be 5%. These guys did 201 subjects and they found 6. So 6 into 200 is 33 per group. They have violated the this rule or advice of 50 per group in a big way. I probably would not have if I had been the statistician on that, I probably would not have found as many slopes on classes. Finally, I'll show you some work by my friend Celia Hybels using the EPIs data set. And here are a better approach of the clusters. The EPIs data set is an old warhorse that we studied. It was a 5146 subjects in Durham and surrounding counties, random sample, and studied over 10 years. And over this 10-year period of time, she finds that the clusters of depression, CESD, they find classes of people who rise a little bit in depression, people who stay the same, which is the biggest group. And this group is slightly rising. That's the biggest group. That's 59%. That's there. 31% were relatively flat. And there is a group of people, 10%, who were decreasing their depression over time. So that is a better use, in my opinion, of this kind of approach. But I give you this idea of latent class trajectory analysis as a way of, as one of the really cool ways, if you have a group of subjects and you want to see, are there different trajectories? And it's one of the things that's obviously used. So I'll stop there. It's 45 minutes. I'll leave 15 minutes to either give you the day back or to answer questions. So let me stop sharing.
In the slide that you had on covariates, you had sort of one beta estimate and then kind of covariates. Wouldn't you actually have a beta per covariate?
Yeah, and at one point I had, I was going to have to explain more matrix stuff. At one point I had it underlined, which to mean a vector, that this beta 3 was a stand-in for a vector of covariates. Obviously, when you do these models, you find that you put a whole bunch of covariates in an epidemiologic situation. You put a whole bunch of covariates into the model, and you get a little beta for each one. So that was just bad notation on my part.
Yeah. Less that though. Then what would that mean in terms of if someone is thinking about a study and designing a study? In terms of thinking about power, as your number of covariates go in, how do you start thinking about power?
It depends. Yeah, it depends upon what you're trying to do power for. If you have your favorite X that you want in the model, then you are always wanting to look at what the relationship between X is, your favorite X, and the Y outcome, or a vector of Ys. You could have multiple Ys, but the point is that you gotta be specific in your question about on one side or the other. You have to be able to say, I want to look at how X impacts it. And there, the covariates, what is the impact of the covariates? The impact of the covariates is they'll reduce variance. And so reduced variance means that that you are going to, one, have a direct effect. The effect is going to be pure because you've controlled everything out in some sense. And second is that if you think about the correlation, how correlation is being computed, it has the covariance of X and Y divided by the variance of X times the variance of standard deviation of X times the standard deviation of Y. But you have now reduced the standard deviation of Y because you've taken out all these variances and the covariances as well. And so what does that mean? It means that you will by covarying in there, by having covariance, then you can detect a smaller correlation given or a smaller effect. And so that typically goes into the power analysis of how much reduction in the variances am I going to get by adding all these covariates. And of course, you're doing that prior in a grant, for example, you're doing that prior. And so you really don't know what that is. And so typically you say, well, the R squared for the covariates will be something, and so I can reduce that variance. And so then this will mean the power that I will actually have. How big a sample will I actually need? Does that make sense?
Yeah, it does. Thanks.
Other questions?
I was going to ask you to say a little bit about power too, to maybe some of the scholars that are often in that position where either you're planning a study and analysis, and if it's a secondary study, you're limited by what's there. You've got the data set that you've got, and you've got to make a decision. Is it worth it to pursue this analysis, or is this a futile errand?
Yeah.
Or you're looking to do prospective data collection, but you're very limited in budget, and in their cases, maybe even time that they're in their residency and trying to,
Right.
they know they won't feasibly be able to recruit many people. So can you maybe just sort of talk as a statistician thinks about what to do in those cases where maybe, you're making a decision, and I know you've helped me with that many times. Yes, exactly.
Yeah. So if you're limited by budget and you say, I can't do this, in fact, you're a pilot study. I mean, that's why you're doing it. And so once you do a pilot study, I propose that you don't get to conduct a test of hypothesis. In the abstract, if you conduct a test of a question, and it's significant, you've done the work. You don't need to conduct the study because you've done it. There has to be a reason why you would continue on but you've already shown that the question has been answered. The second approach is what if you're writing a grant and you're fixed either because you're doing secondary data analysis, or you can only afford to have this many subjects, but you really have to have a test of hypothesis. Then you say, I say you find out what effect size you can detect, and then you appeal to the literature and say, I can, I'll make up something. I can detect a 0.3, and 0.2 has been shown to be clinically meaningful, and so I'm adequate powered, or not, and so that becomes the second part of this. And oftentimes the power analysis just is you have to have a power analysis in most grants. But if you just have a data set and you aren't under grant, the strictures of grant, it is what it is. You go out and test it, and you just can't do anything to find significance. And so that regularly happens, that people come and say, I've got money to study. I don't want to do a pre-hoc analysis. I just want to see what I get. And so I just say, well, let's good travels, brave sailor. Off we go.
Thanks so much, Carl.